Hello my friends and welcome back to the You Can Do TV channel. Melting Solutions, a division of Altec, specializes in advanced aluminum ingot casting systems designed for high performance, automation, and metallurgical quality. The ingot casting process begins after the molten aluminum is removed from the melting furnace or holding furnace. The metal is carefully filtered and degassed before entering the casting line to ensure optimum purity and to remove hydrogen and non-metallic impurities. The molten aluminum is then poured into a continuous or batch ingot casting machine, which consists of a rotating conveyor or belt conveyor carrying molds of standardized ingot shapes. As the molten metal is poured into these molds, tight dimensional tolerances and surface finishes are maintained. After cooling and solidification, the ingots are automatically ejected from the molds and transferred via a conveyor through a solution tank. Then, automated manipulators stack, weigh, and strap. Integrated automation systems monitor temperature, flow, and cooling performance to ensure consistent casting quality. Melting solution systems are designed for high productivity, energy efficiency, and operator safety, supporting both primary and secondary aluminum producers with robust, low-maintenance casting solutions for global foundry operations. The Ras Al Khair Aluminium Complex features a fully integrated production line, starting with bauxite refining into alumina using the Bayer process. Alumina is then smelted via the Hall-Héroult method in high-amperage reduction cells. The molten aluminium is alloyed, degassed, and cast using direct chill DC technology into billets and ingots. Advanced automation ensures precise control of temperature, grain structure, and composition. A downstream rolling mill produces sheets and coils, supporting high-volume, technically demanding industrial applications. Aluminium smelting begins with the electrolytic reduction of alumina, aluminium oxide, extracted from bauxite ore through the Bayer process. The purified alumina is dissolved in molten cryolite inside large electrolytic cells, known as Hall-Héroult pots. A strong electric current, typically over 150,000 amps, is passed through the cell, causing aluminium ions to migrate to the cathode and form liquid aluminium metal, which collects at the bottom of the pot. Once tapped, the molten aluminium is transferred to holding furnaces where alloying elements like silicon, magnesium, or copper may be added to achieve desired mechanical properties. After chemical refinement and degassing to remove hydrogen and inclusions, the metal is cast into ingots, billets, or slabs using direct chill, DC casting, or continuous casting methods. This integrated process ensures high-quality aluminium feedstock for extrusion, rolling, or further precision manufacturing, with strict controls on composition, temperature, and solidification rates. The Buehler Ecoline die casting machine is built for efficiency, precision, and durability. It offers clamping forces from 3,400 kilonewtons to 8,400 kilonewtons, suitable for a wide range of casting applications. The modern injection unit delivers casting speeds up to 8.5 meters per second, ensuring fast and consistent metal fill. Its energy-efficient hydraulic system with low-noise gear pump technology reduces power consumption while maintaining stable operation. The die height adjustment is fast and accurate, and tie bar withdrawal, available in manual or automatic mode, enables quick die changes with improved accessibility. A user-optimized control column features a touchscreen interface with integrated casting diagrams for process monitoring. Integrated die cooling ensures thermal balance. Designed for minimal downtime, the Eco line supports peripheral automation, making it a reliable choice for high-performance, technically demanding die casting environments. Coil coating is a continuous, automated process where a metal coil, usually steel or aluminum, is unwound, cleaned, chemically treated, and coated with paint or film. The coated strip is then cured in an oven, cooled, rewound, and ready for fabrication, delivering uniform, high-quality finishes. At Combi Wear Parts' Foundry, high-performance wear parts are produced through a precise and controlled casting process. It begins with pattern design and mold preparation, followed by melting premium alloy steel in induction furnaces. The molten metal is then poured into sand molds and allowed to cool under controlled conditions. Once solidified, the castings go through knockout, cleaning, and heat treatment to enhance durability. Final steps include CNC machining, quality inspection, and optional surface treatments. These components serve demanding industries, such as mining, construction, and dredging, ensuring long life and reliable wear resistance. BESTONE Tools India specializes in high-precision tool manufacturing, offering a vertically integrated production process from design to final inspection. The journey begins at the office complex, where tooling concepts are developed through advanced design software. Components are machined using VMC, vertical machining centers, and detailed with engraving before proceeding to blanking and forging for initial shaping. Next, parts undergo trimming and punching to refine geometry prior to broaching, followed by profile and shank grinding to achieve tight dimensional tolerances. Post-machining, components are heat-treated for strength, then pass through vibration finishing and electroplating for surface enhancement. Each part is subjected to thorough lab testing, dimensional inspection, and laser marking for traceability. The process concludes with precise packing, ensuring tools are ready for global delivery. BESTONE delivers complete control over quality and performance at every stage. Timber bolt manufacturing at Portland Bolt begins with a 36 mild steel bars, sourced locally in 20-foot lengths. Each cut blank is then heated in an induction coil to around 2,000 degrees Fahrenheit, preparing the end for head formation. The dome-shaped timber bolt head is forged while hot, eliminating the need for washers by providing a wide bearing surface. Next is roll threading, where the bolt is formed between dies without material loss, creating strong, precise threads. This process is faster and more cost-effective than traditional cut threading. Once formed, bolts undergo hot dip galvanizing. Before zinc immersion, they are cleaned in caustic soda and sulfuric acid to ensure surface readiness. After dipping in molten zinc at 840 degrees Fahrenheit, the bolts are centrifuged to remove excess zinc from the threads. Final steps include quenching, inspection, boxing, and shipping to projects like marine construction sites, even remote ones like Hyundai, Alaska. The newly designed Liebherr LC4000 is engineered for gear and profile hobbing of large components up to 4,000 millimeters in diameter. This heavy-duty machine features high-precision axes, dynamic stiffness, and integrated automation options. Ideal for wind energy, industrial gearbox, and large transmission applications, the LC4000 ensures excellent profile accuracy, surface finish, and productivity. With advanced controls and modular tool interfaces, it supports both conventional hobbing and profile grinding operations, delivering flexibility and reliability in large gear manufacturing. Vlukon, a specialized Dutch manufacturer, is renowned for its high-quality pressed steel rims, designed for use in demanding industrial, agricultural, and off-road applications. With decades of experience and a deep focus on customization and durability, Vlukon has become a trusted partner for OEMs and equipment manufacturers across Europe and beyond. The core of Vlukon's operation lies in its ability to manufacture pressed steel rims using advanced hydraulic presses, stamping lines, and precision tooling. These rims are typically formed from high-strength steel sheets, which are cut, shaped, and deep-drawn to exact specifications. Unlike cast or forged wheels, pressed steel rims offer a lightweight yet robust solution, balancing strength with material efficiency. A significant advantage of pressed steel rims is their modular construction, allowing separate manufacturing of the disc and rim sections. These components are later robotically welded or bolted together, enabling flexibility in matching different bolt patterns, offsets, and diameters. Vlukon produces both one-piece and multi-piece rims, including split rim versions for easier tire installation and maintenance. The company's product range includes rims for agricultural trailers, forestry equipment, construction machinery, airport ground vehicles, and even military transporters. Rim sizes range from compact 8 inches variants to heavy-duty 54 inches options, with load capacities tailored to each application. Custom hole patterns, valve placements, and paint coatings, including powder coating and zinc priming, are all available upon request. Vlukon's in-house R&D department and toolmaking workshop allow rapid prototyping and adaptation to customer requirements. From initial CAD modeling to full production, Vlukon emphasizes precision, traceability, and compliance with international quality standards, including ISO certifications. The company's strength lies not only in its production capabilities, but also in its short lead times and small to medium series flexibility. Whether for aftermarket replacements or direct-to-manufacturer supply, Vlukon provides tailored solutions that meet the technical and environmental demands of modern equipment manufacturers. In summary, Vlukon's pressed steel rims represent the intersection of engineering precision, material science, and production efficiency. Their expertise in forming, welding, and assembly ensures that each rim performs reliably under tough operating conditions, whether in muddy fields, rocky forests, or industrial job sites. Through ongoing innovation and close collaboration with clients, Vlukon continues to set high standards in the specialized world of steel rim production. In the heart of Innsbruck, Austria, beneath the shadow of Berg Isel, The Grassmere family has been perfecting the art of bell founding for over 400 years. Their latest masterpiece, a colossal bell destined for the new cathedral in Bucharest, Romania, is set to become the world's largest free-swinging church bell. Standing 3.13 meters tall, 3.36 meters wide, and weighing over 25 tons, equivalent to the weight of 5 adult elephants, this bell is a testament to both tradition and innovation. With walls up to 27 centimeters thick and over 4,000 hours of labor invested, its creation is a monumental achievement in craftsmanship and engineering. The commission for this bell, awarded nearly a year ago to brothers Peter and Johannes Grassmere, represents the pinnacle of their family's 14-generation legacy in bell founding. Since 1836, the Grassmere workshop has been a permanent fixture in Innsbruck, evolving from a traveling trade to a state-of-the-art foundry. Creating a bell of this magnitude is no small feat. The process begins with precise calculations, aided by software Peter Grassmere developed over 15 years in collaboration with universities and institutes. This tool allows the foundry to design bells with unparalleled precision, ensuring perfect tones across various rib profiles. The Bucharest bell, tuned to C0 like the famous Pomeran in Vienna's Stephansdom, but 5 tons heavier, boasts thicker walls that amplify its partial tones, promising a richer, more intense sound. Computer simulations can even preview this resonance, though the true test comes only after casting. The bell's creation involves 3 key components: the core, the false bell, and the mantle. The core, a brick structure coated with clay and shaped by a rotating template, forms the bell's inner cavity. The false bell, a temporary clay model matching the final bronze bell's shape, is crafted next. Using sandy clay that must be loose enough for later removal, workers layer it over the core, supported by ropes to prevent collapse. A thin graphite layer ensures the false bell can be separated cleanly. This labor-intensive process, unchanged for centuries, demands the entire foundry's workforce, with over 5.5 tons of clay shaped by hand. Artistry meets tradition in the bell's ornamentation. Sculptor Konbeckler meticulously models Patriarch Daniel's portrait, chosen to adorn the bell. A plaster mold creates a wax replica, which is affixed to the false bell. Wax letters, pre-made in various fonts and sizes, are also applied to mark inscriptions. These decorations, coated with a special fine clay mixture, a recipe refined over generations, including an unexpected ingredient like beer, ensure a flawless surface. This clay, left to ferment like dough, becomes pliable and ideal for detailed work, a secret passed down through the Grassmere family's historic workbooks. Once the false bell is complete, it is encased in a steel form filled with Furan sand, creating the mantle. Ceramic pipes guide molten bronze from the bottom up, ensuring a dense, high-quality cast. The false bell is then removed, leaving a hollow space for the bronze. After weeks of preparation, the casting day arrives. Over 30 tons of bronze, heated to 1,100 degrees Celsius, are poured from 2 furnaces and a specially designed thermal crucible. The process is fraught with risk. One miscalculation could ruin 6 months of work, A small mishap occurs when clay slips, costing hours, but the team presses on. Patriarch Daniel's delegation attends, blessing the pour in a solemn Orthodox ceremony. After cooling for weeks, the bell is unearthed. The form is broken, revealing a gleaming bronze giant. Its surface is sandblasted for 6 days, and the clapper, forged in Finstal, Germany, by specialists at Rosswag, is installed. Weighing 700 kilograms, the clapper is crafted to strike the bell perfectly, ensuring durability for centuries. When struck, the bell's harmonious partial tones resonate as calculated, a triumph of skill and science. This bell, a symbol of faith and craftsmanship, will ring in Bucharest's Cathedral of the Salvation of the Romanian people, echoing for generations. As Friedrich Schiller wrote in Das Lied von der Glocke, "Joy has God given me," a fitting tribute to a bell built for eternity. The Haas Street 20Y is a powerful CNC turning center equipped with Y-axis and live tooling, allowing both turning and milling operations in a single setup. This reduces handling time, improves part accuracy, and boosts overall productivity. The machine offers 101 millimeters of Y-axis travel, plus or minus 50.8 millimeters from the center line, enabling off-center milling, drilling, and tapping. It comes standard with a servo-driven C-axis and high-torque live tools, providing true 4-axis machining capability. The Saint 20Y supports parts up to 304 by 520 millimeters, powered by a 14.9 kilowatt spindle that runs up to 4,000 revolutions per minute, delivering 203 Newton-meters torque at 700 revolutions per minute. A 12-station hybrid BOT VDI turret is standard, with rapid traverses up to 24 meters per minute, making it ideal for complex, high-precision lathe operations. This operation demonstrates the single setup machining of a 2-cylinder crankshaft from solid 42 CRMOV4 alloy steel, using the Niall Simmons N20 MCX 2000, a high-precision 5-axis turn mill machining center. Designed for heavy-duty applications, this machine integrates multiple machining technologies for complex geometries, without reclamping. The process is entirely cam-free, programmed via custom parametric user cycles developed in-house, enabling rapid adaptation for varying crankshaft designs. Total cycle time, 1 hour 15 minutes. The sequence begins with face turning and center drilling to define part datums. Next, rough turning of the main journals and crank pins is performed using synchronized C-axis interpolation and Y-B-axis positioning, allowing accurate off-center machining at specific crank angles. The machine's B-axis enables tilting of the tool spindle to match the angular orientation of crank throws without repositioning the workpiece. Following turning, milling operations are executed to machine crank webs, radii transitions, and counterweights. Using simultaneous 5-axis control, the tool path smoothly transitions across curved surfaces, maintaining consistent tool engagement and chip load. No part repositioning is required. The crankshaft is fully machined, turning, milling, drilling, contouring, and finishing in a single setup. This eliminates alignment errors, reduces cycle time, and ensures repeatability. The modular cycle system enables parameterized adjustments of stroke length, throw angle, bearing diameter, and web thickness. Ideal for prototyping, flexible small batch runs, or engine development, this setup exemplifies modern high-efficiency complete machining of rotationally complex parts. Deep hole drilling is used to machine internal oil galleries. The high machine rigidity ensures straightness and positional accuracy during extended drilling. Chamfering and deburring are also integrated into the cycle, avoiding secondary operations. The process maintains tight tolerances throughout, supported by thermal compensation, adaptive feed control, and high-performance linear guides. The machine's hydrostatic tool spindle and torque motor drives enable high dynamic response with minimal vibration, essential for surface quality and dimensional stability. The N20MC's integrated tool measurement and probing system further enhances process reliability, allowing in-cycle verification and correction of tool wear or deflection, ensuring precision in every step of the crankshaft production. This demonstrator illustrates how a fully integrated 5-axis turn mill machine like the N20MC can perform complete crankshaft machining with high surface quality, dimensional accuracy, and minimal handling, offering a competitive edge in precision part manufacturing. CNC lathe machining is a highly precise and automated process used to manufacture cylindrical or complex-shaped components from metal or plastic stock. In this process, the raw material is clamped into a rotating chuck, while computer-controlled cutting tools remove material based on a pre-programmed set of instructions. CNC lathes perform a variety of operations, such as roughing, finishing, grooving, threading, and drilling with exceptional consistency and repeatability. Programming is done using G-code or CAM software, which defines key parameters like feed rate, depth of cut, and spindle speed. One of the major advantages of CNC lathe machining is its ability to maintain tight tolerances and deliver excellent surface finishes, even in large production runs. Automatic tool changes and real-time process monitoring further enhance productivity, precision, and operational safety throughout the machining cycle. OMR Group operates globally with production sites in Italy, North America, Morocco, China, India, and Brazil, delivering end-to-end manufacturing capabilities focused on casting, precision machining, and automated assembly for the automotive and industrial sectors. In non-ferrous metallurgy, OMR applies low-pressure die casting, gravity processes, and sand molding techniques to manufacture high-integrity engine and structural components in aluminum. The use of inorganic cores enhances casting accuracy and environmental compliance. Quality assurance is achieved through real-time traceability systems, robot-assisted trimming, and X-ray diagnostics, ensuring internal soundness and dimensional precision. For iron-based parts, the group produces nodular and gray cast iron elements such as brake drums and discs, employing advanced melt control and optimized mold filling. These components are finished using multi-axis CNC systems, configured for high-speed, tight-tolerance operations. Robotic handling and automated gauging maintain process reliability across large production volumes. Machining lines are fully integrated with automated material flow, adaptive control logic, and real-time feedback loops for tool wear compensation and dimensional stability. In assembly, OMR excels in building aluminum space frames using both robotic and manual welding technologies, supported by modular fixtures and automated inspection. Surface finishing, including industrial painting, is executed with strict process control to meet OEM standards. OMR's vertically structured production strategy delivers technically robust, traceable, and ready-to-install solutions with consistent quality across global operations. The manufacturing of wheels and bearings for high-speed railways is a precision-driven process critical to safety and performance. High-speed rail bearings, primarily double-row tapered roller bearings, are designed to withstand extreme radial and axial loads, high speeds up to 350 kilometers per hour, and harsh environmental conditions. The process begins with high-purity steel production, ensuring durability and reliability. Advanced heat treatment techniques, like bainite quenching, enhance bearing life and resistance to fatigue. Precision machining, using CNC lathes and automated grinding, achieves tight tolerances for smooth operation. Bearings are often coated with ceramic or resin to prevent electrical pitting and use high-speed grease for low-friction performance. Real-time monitoring systems, leveraging vibration and acoustic data, enable predictive maintenance, reducing downtime and enhancing safety. Manufacturers like SKF and Timken integrate AI-based diagnostics and advanced alloys to extend bearing lifespan, with some lasting over 1.7 million kilometers. These innovations ensure efficiency, minimize wear, and meet stringent standards like EN 12080, supporting the reliability of high-speed rail systems globally. In modern secondary aluminum production, efficiency, recovery, and process automation are key. The tilting rotary furnace equipped with a vibratory bucket charger is designed for efficient, continuous melting of various aluminum scrap types, including heavily contaminated materials. The side-loading vibratory charger enables simultaneous bucket filling and furnace charging, enhancing productivity and reducing cycle time. Charging occurs through the tilted-up front door, allowing for optimal positioning and controlled material feed into the furnace chamber. The rotary action of the furnace ensures intensive metal slag separation, promoting higher metal recovery rates. During the melting process, pouring, slag removal, and furnace cleaning are all performed through the tilted door position, streamlining operations and reducing downtime. The furnace's design supports easy access for cleaning and rapid slag discharge, minimizing maintenance intervals. This integrated system is ideal for high-efficiency secondary aluminum processing, combining mechanical robustness, process automation, and high thermal efficiency, making it suitable for both batch and semi-continuous operations in demanding foundry environments. At JW Aluminum Rolling operates 24/7 across 4 U.S. facilities to produce rolled aluminum products used in HVAC coils, kitchenware, gutters, and packaging. The process begins with a mix of prime aluminum ingots, at least 99.7% purity, and scrap, including post-industrial and customer-returned material. This blend is melted in furnaces at over 1,000 degrees Celsius. Once molten, aluminum is transferred to a holding furnace, up to 60,000 pounds capacity, then cast into coils using a twin-roll caster. The metal solidifies between water-cooled rolls, forming a cast coil in about 6 hours. Coils proceed to the cold mill for thickness reduction. After an initial pass, they go into annealing ovens to soften the material, enabling further rolling. The process continues through the foil mill, where aluminum is rolled to final gauge at speeds up to 2,000 feet per minute. Coolants control heat and maintain quality. Final steps include slitting, lubrication and testing, tensile, Olsen, elongation. Coils are weighed, shrink-wrapped, labeled and stored with full traceability before shipping, ready to become everyday products like cooking pans or packaging foil. At Niagara Investment Castings, the investment casting process delivers high-precision, near-net-shaped components with exceptional surface finish and dimensional accuracy. It begins with the production of wax patterns created by injecting molten pattern wax into steel dies. These patterns replicate the final part geometry and, for high volumes, multi-cavity tools improve efficiency and cost-effectiveness. For prototypes or short runs, 3D printed patterns from CAD data are used. Wax patterns are then assembled onto a central wax sprue, forming a structure known as a tree. This assembly is repeatedly dipped in ceramic slurry and coated with sand, building a robust ceramic shell mold layer by layer. Once the shell is dry, wax is removed through dewaxing, leaving behind a hollow mold ready for casting. The shell is heated to over 1,700 degrees Fahrenheit, 927 degrees Celsius, and then filled with molten metal. The metal adopts the shape of the mold's cavity, capturing fine external and internal details. After cooling, the ceramic shell is broken away, and the castings are cleaned, cut, and finished. Final steps include grinding, NDT testing, machining, heat treatment, or plating to meet customer specifications. In Ras Al Khair, Saudi Arabia, cutting-edge aluminium rolling meets large-scale industrial power. Designed by SMS Group, the Ma'aden Alcoa complex integrates advanced hot and cold rolling, heat treatment, and automation into one seamless operation, built to deliver ultra-thin gauges, perfect flatness, and consistent high-quality output. The line features a 1+4 hot rolling mill, beginning with 32.5-ton, 635 mm thick ingots, reduced in a 4-high roughing stand, followed by 4 finishing stands to reach 2 to 7 mm strip thickness. A tandem cold mill and single-stand cold mill reduce material further to 0.15 mm with laser-based flatness control, AGC, automatic gauge control, and rapid roll change systems. For automotive grades, a heat treatment and chemical coating line applies precise annealing, cooling, and corrosion-resistant coatings. Full X-Pact automation, real-time monitoring, and plug-and-work simulation ensure seamless control and reduced commissioning time. This setup guarantees consistent strip quality, high throughput, and process efficiency. At the heart of Hyundai Steel's massive Dangjin facility in South Korea lies one of the most advanced large bar mills in the world, where engineering precision meets industrial scale. With an impressive output capacity of 1 million tons per year, it specializes in carbon and alloy steels tailored for automotive and heavy industrial applications. The process begins with blooms measuring 390 by 530 millimeters in lengths from 3.5 to 8 meters, introduced via hot or cold charging into a 200 ton per hour reheating furnace. A high-pressure water descaler removes surface scale before hot rolling. The breakdown mill is a 47-inch, two-high reversing housing with a 1,200 mm maximum roll diameter and 2,600 mm barrel length. Bar manipulators with tilting fingers and hydraulic transfer tables assist in precise material handling. After roughing, intermediate square products are rotated 45 degrees prior to entering the continuous rolling mill. A secondary descaler precedes the 6-stand continuous finishing and sizing mill. The finishing stands feature Red Ring Series 5 technology, offering a 1,030 mm centerline distance and quick change capabilities. The sizing stands, equipped with CGA technology, provide 870 mm centerline spacing for dimensional accuracy. The integrated ProScan laser profile gauge ensures real-time measurement and quality control. Bars are then transferred via exit roller tables to the layer-forming section, followed by turnover cooling beds that continuously rotate the bars for uniform cooling. Finished products include round bars 80 to 350 mm and square bars 85 to 180 mm, formed from billet-sized 150 to 180 mm. At the final stage, cutoff machines with 1,800 mm metallic disc saws handle head cropping and length division, while a 300-ton flying shear adds flexibility. A bar end marking station completes traceability. Bar bundling and binding stations prepare bundles 2 to 10 tons, 4 to 12 meters in length, for shipment. Heat-retaining covers and automated controls enhance efficiency and metallurgical consistency across the entire process. The T&IB manufacturing line begins with feeding pre-cut steel plates into the assembly section. Automatic tack welding secures the components, after which the beam enters the submerged arc welding quickie station. Here, continuous welding is performed on both sides to ensure deep penetration and high structural strength. These heavy sections are temporarily fixed by tack welding before being moved to the next stage. Due to the significant weight of each assembled unit, lifting and transfer operations are performed using chain hoists or overhead cranes equipped with chain slings. The entire system is PLC controlled for precise synchronization between stages. This highly automated production flow allows for efficient manufacturing of T and I beams with minimal manual handling, consistent quality, and high output for infrastructure and industrial applications. Ingot specializes in high-precision mechanical machining for complex components used in energy, aerospace, automotive, and industrial sectors. The company operates multi-axis CNC milling and turning centers, enabling the production of intricate parts with tight tolerances and superior surface finish. Key capabilities include 5-axis milling, CNC turning, boring, grinding, and threading, performed on materials ranging from aluminum to high-strength steels and superalloys. Ingot emphasizes flexibility in batch sizes, from prototypes to small and medium series production. Each part undergoes rigorous quality control using advanced metrology systems. With in-house engineering, CAD, CAM programming, and precision tooling, Novamech delivers reliable, tailored solutions for demanding mechanical applications across Europe and beyond. This machining project, executed on a Herco VMX30 UI using P20 tool steel at 32RC and programmed with Mastercam 2017, showcases the effectiveness of EMUGE's advanced milling tools, combining circle segment and trochoidal strategies for maximum efficiency. The process began with roughing using a 12mm jet cut tool, which removed material quickly across the pocket geometry. This was followed by a 10mm hard cut ball tool, ideal for precision finishing in hardened materials. The transition from conventional to optimized tool paths led to significant improvements in feed rate and cutting dynamics. To further enhance performance, a 12mm multi-cut tool and a 12mm trochoidal cutter were introduced, utilizing high-speed trochoidal paths. These strategies offered smoother engagement, reduced tool wear, and efficient chip evacuation, resulting in a 90% reduction in cycle time compared to traditional methods. Final finishing passes used a 12mm taper form tool and 3/8 top cut tools, achieving excellent surface quality. The complete cycle time for the pocket was reduced to just 36 seconds, demonstrating the value of combining tool geometry with intelligent programming. The Tongbore Mini is a compact, multifunctional boring tool engineered to improve machining productivity and precision. Designed to create near-flat hole bottoms, it eliminates the need for secondary finishing operations. The tool features a dovetail clamping system with a slanted screw design, allowing longer thread engagement. This ensures enhanced clamping rigidity, minimizing insert movement during high-speed operations and improving dimensional accuracy. Ideal for boring, chamfering, and facing in a single setup, Tongbore Mini reduces cycle time and tool change frequency. Its optimized cutting geometry supports smooth chip evacuation, even in small diameter bores. Compared to conventional boring tools, it offers higher stability, better surface finish, and longer tool life, making it suitable for applications in automotive, aerospace, and mold manufacturing, where precision and efficiency are critical. Tungalloy's hard turning series leverages cubic boron nitride (CBN) inserts to efficiently machine hardened steels up to 65 HRC. With dedicated grades like BX820, BX360, and BXM10, the series covers a full range of applications, from continuous cuts to heavy interruptions. Each insert is engineered for excellent wear resistance, thermal stability, and surface finish at high speeds. Ideal for components like gears, shafts, and dies, Tungalloy tools ensure reduced downtime, precise tolerances, and maximum productivity in hard material machining. Kirsten Europe delivers high-precision aluminum bending using advanced techniques: roll bending, mandrel bending, and stretch bending. Roll bending forms large radius curves with uniform pressure via calibrated rollers. Mandrel bending supports the internal profile during tight radius forming to prevent deformation. Stretch bending applies axial tension over a die to eliminate springback and achieve high geometric accuracy. An in-house tool shop designs custom fixtures and mandrels tailored to each project. The facility also offers TIG MIG welding, CNC machining, surface treatments like anodizing or powder coating, and full assembly and packaging. With integrated project management, Kirsten provides complete, technically reliable solutions for construction, rail, and industrial sectors. The Tongue 8mm face milling cutter is designed for low cutting force and high productivity. Featuring 8-edged inserts with a high positive rake angle, it ensures smooth cutting and reduced spindle load, making it ideal for machines with lower rigidity, such as BT30 VMCs. The cutter's large axial rake improves chip flow and surface finish, even in difficult materials like CES 304 or carbon steels like S50C/S55C, perfect for roughing and semi-finishing. Tongue 8mm combines stability and efficiency with extended tool life and optimized performance across a range of materials. The production of corrugated steel sheet, or Profna steel, begins with uncoiling a galvanized or pre-painted steel coil. The flat sheet passes through a series of precision roll-forming stations, which gradually shape the metal into the desired corrugated profile. Each roll station bends the steel incrementally to maintain accuracy and prevent deformation. After forming, the sheet is cut to length by an automatic flying shear synchronized with the production speed. Quality control checks include dimensional inspection and coating integrity tests. The finished sheets are then stacked, bundled, and prepared for transport or direct installation. Thornton Engineering's structural steel fabrication lines in Australia transform 3D models into finished steel components with remarkable efficiency. Each project begins with a 3D model divided into 20-ton job lots aligned with the construction sequence. CNC machines process beams and plates using advanced 3-axis drilling systems with 5 heads per axis, along with high-capacity CNC saws. Each beam is hard-stamped, with a unique part number for traceability. Plates undergo drilling, stamping, plasma, and oxycutting, then deburring. All components pass through a recirculating steel shot blasting machine for a Class 2.5 finish. Final steps include reblasting to remove contaminants and coating in heated paint rooms, inspected by NACE-certified specialists, and delivery. Atlas TiltLab offers a full-service precast solution from tender takeoff through to on-site delivery. All reinforcing steel is locally sourced and complies with New Zealand codes and specifications. Panels are cast on precision steel beds up to 18 meters long, eliminating visible joins and ensuring surface consistency. Curing is accelerated using reticulated hot water systems. Certified concrete is supplied by sister company Atlas Concrete, ensuring material quality. Every panel undergoes strict quality assurance. With minimal limits on size, geometry, or weight, Atlas delivers tailored precast solutions supported by experienced local transport partners. Flame cutting, or oxy-fuel cutting, is a thermal process for slicing thick steel using an oxy-fuel torch. It combines oxygen and a fuel gas, like acetylene, to create a high-temperature flame, preheating the steel to its ignition point, around 1,800 degrees Fahrenheit. A high-pressure oxygen stream then oxidizes and removes the molten metal, creating a clean cut. Ideal for carbon steel over 1 inch thick, it's cost-effective and versatile for construction, shipbuilding, and heavy fabrication. Proper torch setup, gas pressure, and operator skill ensure precision, though the process is slower than plasma or laser cutting for thinner materials.